All right, everyone, welcome back. Dr. P here, and in this lecture I'm going to talk about the Hammond Postulate. Now, what is the Hammond Postulate? Well, I've actually talked about the Hammond Postulate already, I just haven't called it the Hammond Postulate. So remember when I drew that reaction progress diagram, and I'll show you the one in the text here. I drew a full one. Actually, I have it right here. Hold on. This guy here. Remember I drew this, and I said that with the more stable intermediate, we get the faster reaction, and that's the product we get. Well, that is essentially the Hammond postulate. The Hammond postulate states that the structure of a transition state resembles the structure of the stable species closest in energy. The text says the nearest stable species, but it's the stable species closest in energy. So let's say we were looking at this diagram on the left here. Our more stable intermediate is lower in energy than the less stable intermediate here. So our energies for the transition states are going to resemble whatever's closest. So for this slower reaction, the pink here, that transition state, well, its structure is going to look more like the intermediate than the starting material. Actually, the same thing for the green. It's going to look more like the intermediate than the starting material. So essentially what the effect has is the following here. And I'll state the Hammond postulate again. But we can go ahead and have some kind of reaction here. And if I stabilize the intermediate somehow, so if I somehow make this guy more stable, so like on an exam or a quiz, I ask you, what would happen if the energy of the intermediate was slightly lowered? Well, now I'm going to get a lowering of the neighboring transition states as well. Compare that to the case where let's say I lowered the energy of the starting material. So let's say somehow my starting material is more stable. That would actually not affect the peak and the rest of this graph that much. Okay, and that's because the structure of this transition state is a lot closer to the structure of the intermediate than it is to the starting material. So, you know, if you generate a more stable intermediate, it means you went through a more stable transition state to get there. And that's really what the Hammond postulate is about. So, you know, just to sort of restate or paraphrase the Hammond postulate. The structure of a transition state resembles the structure of the stable species closest in energy. The text goes on to say that transition states for endergonic steps, so endothermic steps, typically resemble the product. So this is endothermic here, so that transition state is going to look more like the product of that step, so the intermediate of the overall reaction. Transition states for exergonic steps typically resemble the reactants more closely. And so we can use the Hammond postulate, like I did before, to explain why we get, and again, we'll, I just realized here I forgot to zoom out when I wrote my Hammond postulate. So there's my Hammond postulate. Sorry about that. The structure of a transition state resembles the structure of the stable species closest in energy. Now I'll zoom back in. And just to show you the figure from the text, figure 7.16. And again, we're using the Hammond postulate to explain why the more stable carbocation gives us the faster reaction and gives us the major product that we observe. Okay, so yes, reaction progress diagrams have come back here just for a little bit. We'll probably look at them again some more. But I wanted to have just a short video on the Hammond postulate. And then I think there'll be one more video for Chapter 7. We'll wrap things up talking about rearrangements of carbocations. All right, well, until next time, stay safe out there. Bye now.